Ho, hey, it's Simple Lines Anatomy. Oh, you know what? Yeah, Simple Lines Anatomy now. I got it right this time. Okay, this one we're going to be considering something, analyzing, if you will, something called the GOATA method or methodology. Uh, and that's a an understanding of running and walking and foot weight bearing mechanics. Now I'm going to be doing something a little bit different this time around. I'm going to be doing more of a blind look. That's what we're calling it anyways. And the reality is all I'm doing is not doing my research thoroughly in advance, which is, suicide normally, but we're going for it. We're just going for it this time because I've seen this pop up in my feed, because I follow the people who have come up with this method, or lots of them, anyways, and some of the proponents of it, some of the people who have trained in it, and they've been saying some stuff. And originally, I was like, come on, man, let's get on with this stuff. But they started mentioning some good points, like things that I thought, okay, you got something going on here. And when you start to get your interest tweaked, you gotta follow that. You gotta follow that through. So I am making a theory that I'm going to be able to figure out some of the stuff that they mentioned simply by the fact that I know what I'm talking about. And I'm going to assume they are correct. That's what I'm going to do. I'm going to assume that they have a correct methodology that makes sense, and I'm going to just go for it. That's what I'm going for in this case. Because here's the reality: if you really have something as a methodology, no matter what it is, if your theories, whatever you do, is mostly correct, anyone should be able to take that and figure that out to reproduce the same results. This is the reality of things. You should be able to do that. If you're a good practitioner, if you're someone who really knows what they're doing, somebody should be able to tell you something, and you should be able to prove it right, or should be able to prove it wrong. So in this case, I'm making an assumption here that it's correct. I'm making an assumption, and I'm going to bring up some key points, some things that I have noticed over the last little while, and I'm just going to assume it's true, and I'm going to work my way through some of those major points and see if we can't agree on some of them, because this is a good thing to do if you're studying a subject with any depth. If you want to really understand it, you should be able to come up with the same stuff by going through a similar process. They call this fact checking, double checking, something like that. And doesn't matter what you feel about the subject. You got to do the work. It's easier just to read someone's book. It's easier just to go through it. But if you can reproduce it and say to yourself, okay, this is the reasons they're right, and this is perhaps the reasons they're wrong in some cases, then you've got a better understanding of it. Working your way through it is really, really important. So we're going to go through a few things. Now, one of the things Clark wanted me to mention is that lots of these drawings are from the Simple Lines Anatomy app. That's great, Clark. Good for you, just because you did all the drawings and you wrote all the questions. How nice. Anyways, you can't talk with a deep and melodious voice that can also be annoying and off-key, so deal with that. Anyways, we have to cover a few things first. I want to make one clarification. I will disagree, perhaps until I die, that the foot is the baseline for the body. I will disagree on that fact, and you can challenge me on this, but I have some justification for it. I would say, in fact, everything is the base of the body, every single part. If we want to talk about how structures are unified, how there's a tensegrity model, how there's any of this, how the body works together, and then neurology, bam, we've got so much neurology running through here. We've got so many nerves coming out of these areas, which we will mention shortly. If we want to even know that those exist, we have to understand that everything adds to the base elements. But there is a big consideration, because the problem is that at high speed, the rules change. So if you're really cooking along there, if you're moving fast, the foot becomes more and more important because it becomes an impact point. So I will start to disagree with myself as these things start to take on forces, as the force is applied to and through them, as the force of the body moving on the ground starts to impact at high speeds at incredible weights, in fact, for athletes in particular. it changes. If the foot is not set up right, if we collapse certain elements of it, you're going to see an ascending chain of problems rapidly develop and rapidly cause problems into the system, and you'll start to see problems you wouldn't normally see. So even though I will, right, in many cases, talk about the fact that the foot is not the base of the body, not at all times, it's part of a greater structure, speed changes things, most definitely. And the GOATA method, it is really for in many ways for athletic training. It is for football and anything. Now, it can be applied. Understand that it can be applied to the average person. I don't want to exclude anyone, because some of these are very universal principles that they're talking about from what I've seen so far. So anyways, it should be considered that speed is a big factor in all this. Let me get rid of that. Get rid of some of that. So we're good on that. So definitely understand that the foot is important, and at speed, and weight bearing at speed. Like if you've got, a 300-pound player, the rules start to change between that and just some regular person walking around. Okay, 2 considerations first. One, just real quick, they based a lot of their stuff on natural movement. So in the natural way, people tend to load the foot. In successful people who have done incredibly well in their sports, or whether that's people of cultures that have not been affected by the academic world, the way they load their body, the way that they pressurize these structures, that is on purpose, and they seem to notice the same patterns. These are like hunting cultures that have been unaffected by academic understanding. And I think that's good. The GOATA people seem to have a bit of an issue with the academic world, and I don't blame them. I think there is lots of issues with looking at the body in a straight linear walking motion, as if the leg only swang forward like that, and if there was only hip flexion and there was no circular motion, there was none of this going on, because there's most definitely circular motions going on in the body. We have to consider these things, the internal and external rotation of these joints. It's there for a reason. But some of the problems with the academic world is that when assessing these structures for testing purposes, it is a lot easier to start to eliminate some of the accessories. And if we want to just test the knee joint in isolation, and you need to do that sometimes, if you just want to test only ankle flexion or only hip flexion, you need to eliminate other variables. But it's not an accurate read of the structure and how they work as a unit. So it can miss points in a lot of cases, and that's just how it goes. The studies that are shown, the studies that look at different parts of the foot, maybe they just look at the talus calcaneus joint, or they're just looking at just the arch of the foot. They can be true to a point, but they can miss the bigger picture in a lot of cases. And this is just kind of how these things work sometimes. It doesn't mean they're wrong. It doesn't mean they should be punished or ostracized in any way. It's just that this is how it goes. We're looking at one element, and it's true in that situation, but it's not true sometimes of a greater picture. So I want to say that. Number 2, second consideration, slow-mo video is what they love and they use constantly. And to that, all I can say is yeah, I hope you do. That makes a ton of sense. The slow motion video capture, I believe, came out on the iPhone 5. So if everybody isn't using it, I'd be shocked, because those small, tiny motions happen at such an incredible speed. Let's just say the little contractions, the little adductions of the hip, and the small internal, external rotations, and the way we just load the knee. For instance, these are tiny things. The arch mechanics, how that is up or down in certain phases, the heel strike, the toe strike, the push off. These things happen so fast. If you're not using some kind of a slow motion video capture, you're missing out. That's all. You're just missing out. And it takes time, and it takes effort, and it takes a lot of analysis, but it's well worth it. Ultimately, I would say your goal is always to be able to do the same thing in your head. You should be able to see some of these tiny little mechanics inside your head occurring, even though it's minute, even though it's very, very small. You should be able to understand the big and small motions, and you should be able to visualize them in your head. You should be able to see them happening. And when you can do that, you have a better understanding. But back it up, though. Back it up with video capture that makes sense out of it and makes makes it understandable and easily digestible for the average person too. That is another fault of academia, is making something overly complicated. But let's not go on about that. All right. Big key points. I've just picked 3, and I'm going to just say right now, if you're a proponent of the GOATA method, if you came up with it yourself, I don't know if anyone's going to watch this, but if you have an understanding of it, I'm going to miss a bunch of stuff. And that is on purpose. I promise you, I did that all for a reason. I am not looking at this. I'm going to miss a whole bunch of things, but I'm going to see if I can prove these things to be true without a detailed understanding, because it should be universally true. So if you want to come in the comment sections and it's like, you missed this and you missed this and you missed this, it's like, yes I did, without question. You are absolutely right, and I'm good with that. So you're still going to comment anyway, so whatever. All right, here's a big thing right here. Let's look at the foot. Let's start with something real simple. For the first post I saw, they started mentioning loading the outside edge of the foot. Loading this, they call it an outside edge. I'm good with that. It's this part here. To which I said, I missed that. Why didn't I see that? That's an obvious one. Now, I'm not really a sports person. We're an anatomy and biomechanics group, and that's what we like to look at. But it was one of those things. Is like, yep, it's designed for that. The foot is very clearly designed for that. So let's start with this. That's an arch. That is an arch right there. Sort of, kind of, not really. I'm going to disprove that in just a second. But look at how this point is high, and look at how this is the inside. This is the inside. And look at how the outside of the foot, there's the outside edge. That's low. So high versus low. We have bone contact, and we're all pretty much like this right from the start. As soon as a kid starts walking, they are in this position. Not always like immediately when we're born, but mostly you got this high point here, this big whoop there, and then this point here, this bone that's coming very, very close to the ground. So let's just take, as an example, take the calcaneus, for instance, this amazing bone right here. It's the same bone, just from 2 different angles. And you would think, look at the size and the breadth of this. This is a great thing to load when we're standing. It's a good thing. It makes a lot of sense to load that because it's bone and it's durable and it can take that load. But as soon as we get to more of the inside edge of the foot, it's tissue. It's a fascia, plantar fascia, and it's muscles. The problem with muscles and fascia is they can only be loaded for so long before they will deform under weight. They will deform under pressure. So the calcaneus makes sense to load, but it doesn't really make sense to load this structure for long periods of time. If we're just standing, I'm just talking about standing here. Or if we're running at a really good speed, we're going really, really fast, it doesn't make sense to load it excessively because it will wear down, especially with long-term use, say in sports or running, like marathon stuff. So instead, their theory, these are most of their words, we load the outside edge of the foot because it has bone contacts. It's very important that it has that because it can stand up to the test of time in a way that muscle won't and fascia won't. It will deform, bone will deform, but it will deform slower, and it will reinforce itself in a bit of a different way than we have with these guys in here. It also doesn't exhaust in the same way either, which is nice. We want to maintain this stuff because it's a propulsion mechanism. We'll get into that later. So bone should be loaded. So now I have to dispel a bit of a rumor. Now this is just me. I'm sure other people have said similar things to it, but I'm going to say right now the foot is not an arch. I'm not even going to say the foot is a series of arches because, the books will say that. They'll say there's an arch here, and there's an arch here, and there's like another arch here. That's good. That's okay. The foot is a dome. The foot is a dome structure. So if you've seen a dome, it's, something like this. It goes like that, and then it will have a domed thing getting smaller. Hopefully, God, I hope that makes sense. Okay, so let's add some shading to make it worse. So compare a dome to a bridge. A dome has a high point and then lots of low points all around it. So it has a circumferential support structure, whereas an arch, a single bridge, would have a structure like there's its fixed point into the ground, there's the actual bridge structure, and there's its other fixed point into the ground. So the bridge naturally wants to expand out this way as it's weighted down. And so it has two major support structures, two major fixed points that are on the outsides of that bridge. So it prevents collapse by pushing on those 2 points. Domes don't do that same thing, because we do have an arch here. If you reduce it down to a single plane, if you just do a slice, it looks like an arch. But when you look at the whole thing, look at this. We've got our high point here, and we've got our low points all around that dome. It's a dome-like structure. So when a dome gets pushed down upon, when the weight is pressurized, all of these contact points, and it's not going to be every single part of the bone, but all of these contact points prevent the collapse of the arch. So automatically, the fact that we have low points of bone all through here makes sense that we should be weight bearing on that more regularly. It doesn't mean that this part can't take expansion and contraction. It doesn't mean it can't take the weight. In fact, it needs to take the weight on regularly, but it needs to take the weight on intermittently. That's an incredibly important element to it. It's not made to be sustained over long periods of time. If it was, we would just fuse the whole structure. It would just be a large chunk of bone right there. It would be solid the whole way through. Why have it move? Instead, we put muscle and fascia, which can be exhausted with long-term use. So it needs to be used intermittently. Muscle and fascia must have rest cycles to recover the necessary energy for them to keep working. So that's very important. So the outside edge loading of the foot, perfect sense to me. That one was a piece of cake. Okay, point 2, heel away is what they say. Heel away all day, I think it's called. And sports people, I don't know, you probably don't want to hear this, but that's adorable. You just come up with these sayings sometimes. You didn't want to hear that at all, but it's heel away all day. I love it. Anyways, so the heel's coming back kind of like this. So we're walking, and everybody, nobody's going to argue that the foot comes up as we step off. The foot goes back and it bends up, and it's like, right about here, right? So there's our foot in flexion, so the knee flexion part. That's an easily understandable part to it. And again, that's a linear understanding though, but there are curvatures involved in all this. If you miss those curvatures, you miss the bigger, more complex, detailed motions of the human body. That is one of the worst feet I've ever drawn. I got to get rid of that immediately, because I never want to see that again. Okay, we're back. We got this. So heel away all day. So it's coming back, but at the same time, it is coming this way as well. So it's coming as if it were going like here. Hopefully this makes sense. 3D with the power of computers. Ugh. Ugh. Okay, you get it. Anyways, you get it. So it's coming back, and it's coming in. You could say it's coming in a little bit. It's a fine way of saying it, but this is technically, just to be clear, this is technically external rotation of the femur. Just if anyone wants to correct me on that, just so we're all on the same page. It is external rotation of the femur. Just, in case someone wants to yell loudly. But what that does, it is setting up some important mechanics. It is actually setting up some really important things by doing this. So what I will in fact start with, I'm gonna take a jump. Again, I didn't have the GOATA people tell me this, but I knew this in advance, and I think other people have explained the same thing. But we've got some naturally paired motions in the body. So there is an area in the spine, and it's about L2 to 4. So there's T12, just so we're clear. There's L5. There's 4, 3, 2, and they make up 2 main nerves. I'm just going to draw one for clarity's sake. They make up 2 main nerves that we call the obturator and the femoral. I'm going to leave those out. I'm not going to draw those in. And the obturator and the femoral come from the exact same spot in the spine. So they are the control nerves to all this stuff that's going on, to a bunch of different muscles. They go to, for instance, the flexor muscles of the hip. So rectus femoris being a big one. So there's rectus femoris, give or take right there. I could do better. There we go. There's rectus femoris. And it goes to the other vastus muscle. There's about 3 of them. I'm going to leave them out of the picture just so we're clear. And that one goes to there. So it's going to do knee extension, for instance, and a bit of hip flexion. So when we're back like this, understand that when we're back all the way here, it's going to be the rectus femoris that helps bring that knee into a straightened position. Because we're all the way back here, the next phase is to go forward. Again, that's linear sagittal plane motion. It's still relevant though. Let me just cut some of this out because now we don't need that anymore. That's useless to us. So rectus femoris. So hip flexion starting into knee extension. That's going to be kind of the next phase. Now, the other thing that the obturator, this would be obturator in this case, it powers what's called the adductor muscles, and that's adductor magnus, great name, adductor brevis, and longus. And I'm just going to draw it in a very simplified way, but they adduct the leg. So I'm going to say, as we're going through our gait cycle, as we start walking, really simplified picture, and this is walking or running. As we are going to be walking, there's just a simple hip, there's a simple leg and a foot, and then the opposite side, leg, foot. It's important that these things work synergistically, or they work together. So if this is hip flexion here, this is knee extension here, understand? So it should be paired together. Those 2 motions are paired. You can read the anatomy and neurology like a book if you study it hard enough. So that tells me the fact that those 2 areas, the L2 to 4 gives you both flexion and adduction. Flexion, knee extension, hip flexion, knee extension, and hip adduction, which is going that way. That's hip adduction, adduction. There we go, going that way. They should happen together. And by putting the foot, the heel away, what we call femoral external rotation, or bringing the foot in, that sets up a much needed mechanic that makes the foot come and swing through adduction quite naturally. So it's proven, this point is actually proven in the anatomy and the neurology, because what we want is a nice smooth movement. So this is the feet here. I'm going to shrink this down through the magic of computers. I'm going to snatch that up, grab that, put it down. There we go. So these are some feet. Now, what I'm going to describe is some of the circular mechanics that are going on, some of the circles that are happening in the foot. That's the wrong color. Color match. There we go. Okay, it's got to be good. We're not even close. Okay, whatever. You get the idea. Okay, so there's some more feet. You can see they're loading that inside edge. Close enough. That's good. Hey, that'll be foot 2. Okay, so what we want, because of these paired motions, what you don't necessarily want is one foot just perfectly replacing the other. You don't want just a straight line here. And though that's sort of the given method that's explained a lot, it's not really what the body wants to do. What there should be is a little bit of a swing through, a little bit of that. So that is, as the hip is flexing and the foot is coming forward and the knee is extending, there should be a bit of adduction, and that should be happening. And this is a setup mechanism. This makes it happen much more effectively. So they're doing that. The feet are coming close together. See this overlapping part? Obviously you're not kicking your own leg, but it's setting it up. Now the heel away is not necessary when you're walking. The adduction most definitely is. The foot, the whole leg has to drop in like that. That's important for normal mechanics to happen. But at high speeds, we have to get that swing through happening involuntarily. This is super important in sports training. The more you can make it so that your athletes do the right thing without having to think about it, the easier it will be for them, the less trouble they will have in doing those actions. It's why we train so much, why prep work and training. And you know, you look at the GOATA people, there's lots of videos of them practicing with small implements, little basically boards, what I've seen, Again, I know very little. Basically, boards that look like that, and the foot is placed, and they practice loading it on the outside edge so that it becomes involuntary. There's a heel, and there's a foot, and there's some toes. It's one of the worst pictures I've ever drawn, but I'm sure I will top that shortly. Okay, so they practice loading. So that's just the truth of all athletics. It's the truth of any true practice. Martial arts is a great example of that. Yoga is a great example of that. These are things we have to do to get good at something. Any proper mechanics that can be made involuntary, that's good. That's what we want. Okay, let's get rid of this. Point three I definitely want to make. Injury prevention. What a great goal. Honestly, yeah. Why wouldn't you? So I'm gonna bring up one. I'm gonna just show a simple example. I'm gonna go after the Achilles in this case. So the problem with the Achilles in loading it or collapsing the arch. That's ultimately what they have found in their training of athletes, is that injuries tend to happen around people's arches collapsing. So this arch that used to be robust and nice like that, well, unfortunately now it is not robust and nice. It has just done that. It is flattened right out. So these bones here, they have shifted down. They've gone like this, and the foot has gone like this, and then the calcaneus is somewhere here, and the talus is somewhere here. So we've just lost that arch entirely. And again, it's very easy just to go, that's not a big deal. But it makes a little more sense to go, if we all have it, it's probably there for a reason. And maybe it won't kill you to have a poor arch initially, but given enough time and given enough pressure, you start to see problems show up when we lose one of the natural mechanics of the body. Even though it's not going to blow the knee apart immediately, it probably has something to do with our overall sustaining capacity. So even though it's small, it is important. Okay, I'm going to talk about the gastroc. I'll mention the ACL and the MCL just quickly, but this is what I've worked out, which I think makes most amount of sense. So the arch has collapsed. Let's just say the arch has unfortunately met its end, and now it's going in like that. I'm exaggerating heavily, but the arch, we've lost it. It is pressurized usually this way. That's going to be where that's coming from. So we're loading the foot wrong. We're loading it on that inside edge here, and that inside edge, as all fascial tissues will, whether that's ligaments or muscles or planes of fascia, they will yield and deform to their stretch, and they will take on the length that you force it to have. So the arch is collapsed. Now, really, really simple. I'm going to keep this as simple as I possibly can. As I collapse the arch, the distance between the two attachment points starts to increase, because we're turning that foot, we're turning it over just a little bit. It's going into not just the arch, but the ankle is going into internal rotation, as if it were coming like that. Hopefully that makes some sense. We've lost that arch. So the distance between point 1 and point 2 has increased. And it's not just the gastroc, because it's easy to just go after gastroc, but we've got this whole soleus muscle back here that also feeds into that Achilles too. And in fact, that can be just as important. So looking at it now from the lateral side, so that was a posterior view. We're going to go lateral. If this is the gastroc here, attachment like so, origin, insertion, there we go, better circle. And then for the soleus, origin, insertion. There we go. As this distance increases, the strain, the resting strain happening on the muscle also increases. Now, that's not necessarily a problem in the short term. You could have this for your entire life and never have an Achilles tear. But again, this is for athletes. In fact, actually, you could have this. Plenty of people have this, and their Achilles do eventually tear, and maybe that's the cause, but I don't know. In any case, but this is for athletes, and they will be loading this structure. They will be loading the structures in ways we wouldn't normally. So let's say we're running. We're really moving now. We're all going forward. The knee is wanting, this is the step. We're coming through on the step here. The ground is somewhere around here. We're coming through on that step. We're rolling on that foot. We're headed in the forwards direction. And we need to take that knee that is in a bit of a flex position, and we need to extend it. And believe it or not, like we're trying to push our legs straight. Believe it or not, we need to bring this tibia back. If we don't, we're gonna roll over our entire knee and we'd probably obliterate it. So that would be bad, just so we're clear. But as we're loading it, the pressure is also down. So there's part of it that's driving that tibia forward. So these muscles actually become resistors of the tibia going forward. So the tibia, because of the weight of the body, the whole body is going like that. It's going over the ankle. So the tibia is being pushed down and forward, but it needs to be brought down and back. And so the gastroc and soleus, those calf muscles, they are in the exact right position to do so. They are bearing a lot of weight at this exact moment. And so if you were to load hundreds, literally hundreds of pounds of pressure and more in a bigger player, you would see that the strain and the force running through these tissues is quite extreme at that moment. It's a small period of time. It's only a small period of time that this is happening, but it's still relevant because we're moving fast enough and there's enough force coming through the body at that exact moment. So it is very relevant. This is, again, why slow motion video or understanding of the small, minute, like tiny duration mechanics is very important. You wouldn't be able to see it otherwise. So as this whole Achilles is being loaded, if we are not loading the foot right, it accentuates quite drastically because of this arch loss. It accentuates quite drastically the strain on the Achilles. And what can happen, and this may not be a long-term thing, what can happen is we start to get a rupture in the tissue. Now, what would more than likely precede this is we would build up thickenings in the fascial parts of the structure. We would build up basically fibrotic tissue. And I do believe they've mentioned this using different words. We start to build up fibrotic tissue in the structure, and that means the muscle no longer expands, so it doesn't do this anymore. It doesn't lengthen properly. We lose that ability. So the force is then placed on the next structure in line, and that can be the knee, so it explains some of the ACL, MCL stuff, but it also gets placed on the Achilles, and we might see a rupture occur here, a ripping and a tearing of these structures. The Achilles, which is really a double, again, it's a double tendon of both the soleus and gastroc. So this is where I would fully agree. Now, as we alter these mechanics too, again, you can make more considerations very, very quickly as you load the body this way, as the pressure is this way, especially in a little bit of a flexion. The femur wants to displace from it. And because we're loading the body as well, let me get rid of some of this, pardon me. So as we're loading the femur that way, and the tibia is being pulled this way, if there is more strain, if there's more strain in twist, it means that it's collapsing in this direction. The tibia will be more brought this way. So not only do we get ACL strain, which is here, again, this is very minute, sorry, ACL, there we go, ACL and PCL, let's throw that in there, but ACL, we also get medialward strain relative to this structure. So we're getting some points where the ACL and the MCL and the meniscus, of course, that's there too. They're being strained a little bit more than they should be, a little bit more than they normally would be. So this is well worth a consideration. In the future, I'm hoping to do a more detailed look at this. In any case, I'm happy with that. Hopefully it made sense. This has been Simple Lines Anatomy. Find us on these social media sites. Maybe check out our app. It's pretty good. Have dinner with us sometime. You know, we're cool. We hang out.